Now, hi everyone, welcome back to the Comptia Network Plus course, Virtual Router Redundancy Protocol. Like HSRP, Virtual Router Redundancy Protocol VRRP allows a group of routers to form a single virtual router in an HSRP or VRRP group. One router is elected to handle all requests sent to the virtual IP address. With HSRP, this is the active router, and an HSRP group has only one active router, at least one standby router, and many listening routers. A VRRP group has one master router and one or more backup routers. That is the open standard implementation of HSRP. Comparing VRRP and HSRP. The LAN workstations are configured with the IP address of the virtual router as their default gateway, just as they are with HSRP, but VRRP differs from HSRP in these important ways. VRRP is an IEEE standard RFC 2338 for router redundancy. HSRP is a Cisco proprietary protocol. The virtual router that represents a group of routers is known as a VRRP group. The active router is referred to as the master virtual router. The master virtual router may have the same IP address as the virtual router group. Multiple routers can function as backup routers. VRRP is supported on Ethernet, Fast Ethernet and Gigabit Ethernet interfaces, as well as on multiple multi-protocol label switching, MPLS, virtual private networks, VPNs and VLANs. VRRP redundancy characteristics. VRRP has some unique features. VRRP provides redundancy for the real IP address of the router or for a virtual IP address shared among the VRRP group members. If a real IP address is used, the router with that address becomes the master. If a virtual IP address is used, the master is the router with the highest priority. A VRRP group has one master router and one or more backup routers. The master router uses VRRP messages to inform group members of its status. VRRP allows load sharing across more than one virtual router. Advanced IPv6 concepts. Before we jump into the coverage of IP version 6 routing protocols, we need to discuss some of the operations that are performed differently in IP version 6 than in IP version 4, and that includes several operations that are radically different. We'll also discuss in the following sections some of the methods that have been developed over the past few years to ease the pain of transitioning to an IP version 6 environment for one that is Ip4. Router advertisement. A router advertisement is a part of a new system configuration option in IP version 6. This is a packet sent by routers to give a host network ID called a prefix IP version 6 so that the host can generate its own IP version 6 address derived from its MAC address. To perform auto configuration, the host goes through a basic 3-step process. 1. First, the host needs the prefix information similar to the network portion of an IP version 4 address to configure its interface, so it sends a router solicitation RS request for it. The RS is then sent out as a multicast to all routers FF02/:2. The actual information being sent is a type of ICMP message, and like everything in networking, this ICMP message has a number that identifies it. The RS message is ICMP type 133. 2. The router answers back with the required prefix information via a router advertisement or a router advertisement message also happens to be a multicast packet that's sent to all the nodes multicast address FF02:1 and is ICMP type 134. Our router advertisement messages are sent on a periodic basis, but the host sends an RS for an immediate response, so it doesn't have to wait until the next scheduled RA to get what it needs. 3. Upon receipt, the host will generate an IP version 6 address. The exact process used, stateless or stateful auto configuration or by DHCP version 6 is determined by instructions within the router advertisement. By the way, the host generates an IP version 6 address using the prefix and its MAC address. The process is called stateless auto configuration because it doesn't contact or connect to and receive any further information from the other device. Take a look at figure 10.6. In this figure, the branch router needs to be configured, but I just don't feel like typing in an IP version 6 on the interface connecting to the core router. I also don't feel like typing in any routing commands, but I need more than a link local address on that type of interface, so I'm going to have something special. So I basically have the branch router work with IP version 6 on the internetwork with the least amount of effort for me. So here you can see, here's the figure 10.5, first two steps IP configuration. So here we have step 1, host sends RS message FF02 -2 ICMP type 133. Router 2 sends RS message FF02:1 ICMP type 134. Host receives the router advertisement and included prefix, allowing it to auto configure its interface. Neighbor discovery. One of the biggest changes in IP version 6 is the discontinuation of the use of all broadcasts, including address resolution protocol broadcast. Devices use a new process to send to one another within a subnet. They send to one another's link local address rather than the MAC address. Even devices that have been assigned an IP version 6 address manually still generate a link local address. These addresses are generated using the MAC address as is done in stateless auto configuration. The prefix is not learned from the router. A link local address always adopts a prefix of FE80:/64. That means that rather than needing to learn a MAC address to send locally, the host needs to learn the link local addresses of all other hosts in its subnet. This is done using a process called neighbor discovery. This is done using neighbor solicitation messages and neighbor advertising messages. These are both sent to IP version 6 multicast addresses that have been standardized for this process. Neighbor solicitation messages are sent on the local link when a host needs the link layer address from another node. See figure 10.17. The source address is a neighbor solicitation message is the IP version 6 address of the node sending the neighbor solicitation message. The destination address is the neighbor solicitation message is the solicited node multicast address that corresponds to the IP version 6 address of the destination node. The neighbor solicitation message also includes the link layer address of the source address. The destination node replies by sending a neighbor advertisement message which has a value of 136 in the type field of the ICMP packet header on the local link. The data portion of the neighbor advertisement message includes the link layer address of the node sending the neighbor advertisement message. A source node receives the neighbor advertisement. The source node and the destination node can communicate. Tunneling. When tunneling is used to transition mechanism to IP version 6, it involves encapsulating one type of protocol in another type of protocol for the purpose of transmitting it across a network that supports the packet type of protocol. A tunnel endpoint, the packet is de-encapsulated and the contents are then processed in its native form. Overlay tunneling encapsulates IP version 6 packets in IP version 4 packets for delivery across an IP version 4 network. Overlay tunnels can be configured between border routers or between a border router and a host capable of supporting both IP version 6 and IP version 4. Cisco IOS supports the following tunnel types: manual routing encapsulation GRE 6-4 and ISATAP. GRE tunneling, although not used as an IP version 6 transition mechanism, generic routing encapsulation tunnels are worth discussing while talking about tunneling. GRE is a general purpose encapsulation that allows for transporting packets from one network through another network through a VPN. One of its benefits is its ability to use a routing protocol. It can also carry non-IP traffic, and when implemented as a GRE over IPsec tunnel, it supports encryption. When this type of tunnel is built, the GRE encapsulation will occur before IPsec encryption process. One key thing to keep in mind is that the tunnel interfaces on either end must be in the same subnet. 6-4 tunneling. 6-4 tunneling is super useful for carrying IP version 6 data over a network that is still IP version 4. In some cases, you will have IP version 6 subnets or portions of the network that are all IP version 6, and those networks will have to communicate with each other. This could happen over a WAN or some other network that you do not control. So how do we fix this problem? By creating a tunnel that will carry IP version 6 traffic for you across the IP version 4 network. Now having a tunnel is not that hard and it isn't difficult to understand. It is really taking the IP version 6 packet that would normally be traveling across the network, grabbing it up and placing an IP version 4 header on the front of it that specifies an IP version 4 protocol type of 41. When we're configuring either a manual or automatic tunnel covered in the next two sections, three key pieces must be configured: the tunnel mode, the IP version 6 tunnel source, and the 6-4 IP version 6 that lies within 2002:/16. Manual IP version 6 tunneling. In order to make this happen, we're going to have a couple of dual stacked routers. We just have to add a little configuration to place a tunnel between the routers. Tunnels are very simple. We just have to tell each router where the tunnel is starting and where it has to end. Let's take a look. The following configuration creates what is known as a manual IP version 6 tunnel. So router 1 config hash int tunnel 0. Router config if hash IP version 6 address 2001 DB8 1/1/1/1/64. Router 1 config if hash tunnel source 192.168.30.1. Router 1 config if hash tunnel destination 192.168.40.1. Router config if / tunnel mode IPv6 IP. Okay. Router 2 config hash INT tunnel 0. Router 2 config if IP version 6 address 2001:2:2:1/64. Router 2 config hash tunnel source 192.168.40.1. Router 2 config if tunnel destination 192.168.30.1. Router 2 config if hash tunnel mode IPv6 IP. This will allow our IP version 6 networks to communicate over IP version 4 network. Now, this is not meant to be a permanent configuration. The end goal should be to have an all IP version 6 network end to end. 6 to 4 automatic. The following configuration uses what is known as automatic 6 to 4 tunneling. This allows for the endpoints to auto-configure an IP version 6 address where a site-specific /48-bit prefix is dynamically constructed by prepending the prefix to 002 to an IP version 4 address assigned to the site. This means the first 2 bytes of the IP version 6 address will be 0x2002 and the next 4 bytes will be the hexadecimal equivalent of the IP version 4 address. Therefore, in this case, 192.168.99.1 translates to 2002:C8:6301:/48. Tunnel interface 0 is configured without an IP version 4 or IP version 6 address because the IP version 4 or IP version 6 addresses on Ethernet interface 0 are used to construct a tunnel source address. A tunnel destination address is not specified because the destination address is automatically constructed. It is also possible for each tunnel to have multiple destinations, which is not possible when creating a manual IP version 6 tunnel. Router config a hash interface Ethernet 0. Router config hash IP address 192.168.99.125.255.255.0. Router config if hash IP version 6 address 2002:C0A8:6301:/48 extended unique identifier 64. Router config hash exit. Router config hash interface tunnel 0. Router config if hash no IP address. Our router config if hash IP version 6 unnumbered Ethernet 0. Router config tunnel source Ethernet 0. Router config hash tunnel mode IP version 6, IP 6 to 4, router config if / exit. When using 6 to 4 tunnels, when using 6 to 4 tunnels, in many cases you will need to reference the tunnel endpoint when creating a neighbor statement. For example, in Border Gateway Protocol, when doing so, you can refer to the auto-configured address in the preceding example in 3 ways in the neighbor command: :C0A8 :6301 :192.168.99.1 0:0:0:0:0:0:192.168.99.1 to configure a static route to a network that needs to cross a 6 to 4 tunnel. Use the IP version 6 route command. When you do this, the least significant 32 bits of the address referenced by the command will correspond to IP version 4 address assigned to the tunnel source. For example, in the following command, the final 32 bits will be the IP version 4 address of the tunnel 0 interface: IP version 6 route 2002:/16 tunnel 0. So I'm going to leave it here today for this video. If you liked listening, please consider sharing and subscribing. Thank you.